All right, this is the 14.8 video. As you can probably tell, I am back in my kitchen because of my 4th of July project that messed up my sunroom. So I'll tell you about that later in the video, but in case you're wondering why it's brown instead of white, it's because I'm back in the kitchen. So 14.8 is on substitutions and multiple integrals. This is not substitution like U substitution. This is substitution in 2 dimensions. So U substitution that you learned in Calais was in 1 dimension. It was substituting just a U. And this is substituting in 2 dimensions in that you're going from something in the XY plane to something in the UV plane. So it's like a UV substitution. But in addition to substituting the function like you do in a regular U substitution, you have to change the bounds. And so what happens is before, if you changed the bounds in a U substitution, you could just plug it in and get the new numbers, but now you've got to find a whole new region. So because double integrals, which is we're going to be doing, here's some double and then there's some triple ones later. Because we're going to be doing double integrals initially, double integrals you're integrating over a region, which is 2-dimensional. And so you've got to find a whole new region to get all 4 new bounds instead of just 2 new bounds like a U substitution. So it's significantly more complicated, obviously, but that's kind of the general idea. So they have a picture here just so you can kind of see an example. So this would be in the, why are you not focusing? Okay, there we go. This would be in the XY plane. And then what you would do is you would figure out, okay, the region R, which is in the XY plane, corresponds to some region G in the UV plane. And notice the shape does not stay the same. It could be going from a circle to a square, or I mean, who knows what it can be. It doesn't have to be the same shape. Okay, but what you have is you have X is a function of U and V, and Y is a function of U and V, and so you can go actually back and forth between the two. So I talk about that a little bit here in the margin, and that's kind of what we're doing. So I'm not going to read this to you, but let me just point out what you should read. This is page 814. So some information at the top of the page. Here's the U and V. They're talking about G is the region in the UV plane. So whenever you see a G, you know that's the UV plane. Usually they use R for the XY plane, but occasionally they use D. If you're going to do polar, they'll use D. So that's the only thing that's different. But just like in polar, speaking of polar, if you remember in polar, which is 2-dimensional, which is a double integral, sorry. A double integral is polar. They had that extra piece that popped up when you changed from Cartesian to polar, is that R. Remember the R, dr, d theta? So whenever you change from one coordinate system to another, an extra piece is usually going to pop up. Like when you do a U substitution, you usually have that extra piece that cancels out your x's, right? That's the extra piece that comes up when you make the substitution. Or in both polar and cylindrical, you had the R that popped up, and in spherical, remember you had the rho squared sine phi. So for these, just for a generic transformation, those are specific transformations. Polar, cylindrical, spherical, those are specific transformations. These are generic transformations. And so what they have for their extra piece is this piece right here. This it's a function of U and V, unless your derivatives are numbers, in which case then it's going to be a number. But it could be a function of U and V. It's called the Jacobian. The Jacobian. So that's the extra piece that's going to pop up. And just, I'm going to skip ahead and show you something interesting while we're talking about this. They have on page 819, this is 3 dimensions, we'll get to that in a second, but notice they have in example, well, it's not really an example, just on this page, they show you how the extra piece pops up for the R in cylindrical, and how the extra piece pops up for the rho squared sine phi in spherical. So just so you can see the connection, it would be the same things that would pop up as you had them before. But again, those were specific cases, so you knew it was going to pop up, and these are general cases, so we don't know. So anyway, there's a lot of information. Please go back and read this, or pause the video and read it now on page 814. See all of this highlighted stuff, lots of stuff to read. But what you're going to be doing is you're going to be changing your region R in the XY plane to region G in the UV plane. You're going to be changing your function from a function of X and Y's to a function of U's and V's. And then when you change your dA is either dx dy or dy dx. When you change your dA over, it's either going to be du dv or dv du, but you're going to have this extra piece, this Jacobian, that pops up. So it's just like going from Cartesian to polar, or Cartesian to cylindrical, or Cartesian to spherical, except that now you don't know the equations that relate them, like cylindrical and Polar, you know x is r cosine theta, y is r sine theta, etc. Here you don't know those equations that are going to connect the x and y's to the u's and v's, and you also don't know what the extra piece that's going to pop up is, so you have to actually find it. So they talk here a little bit about the Jacobian, and then this is the two-dimensional form of the Jacobian. We'll see the three-dimensional form in a second. But notice what it is. X is a function of u and v, y is a function of u and v. So the top row of the Jacobian, this is a determinant, the top row is the partial derivatives of x. And notice it's alphabetical order, going across and down, alphabetical order. So x is on the top, and then y's, and then left to right, u's, and then v's. So when you set it up in the determinant, alphabetical order all the way. Then you're doing the cross like you do with cross products. So you're doing dx du times dy dv, and you're doing dy du times dx dv, and then you subtract, right? So this is just like a regular piece of a cross product determinant. So that's how you find the Jacobian. Okay. So they have some examples in the book. I have a few examples obviously in my notes, but because this is a little bit weird and it takes a little while to kind of get the hang of this because it's just so different than what you've done before, they have several examples in the book. So example 1 is finding the Jacobian. Example 2 is applying a transfer. These are called transformations, like U substitutions, but you're doing a transformation, so they call it transformations. Example 3 is another one. Example 4 is another one. So they have several. So if after watching this video, if you still kind of feel iffy about this stuff, look through the examples in the book. They have several more. But here on page 818 is the stuff for triple integrals. So notice now you have a third variable. X is a function of u, v, and w. Y, u, v, and w. Z, u, v, and w. And so just to keep from having to write this huge thing down here, they just call this h. So when you change the function here, this capital F is a function of x, y, and z. When you change it over to be a function of u, v, and w, they're just calling that h, just to keep from having to put this huge thing right here. Okay, so they're using d because this is now a three-dimensional region that you're integrating over, but they still use g for the transformation. So for the in this case in the UVW plane, and so you have now again three-dimensional pictures, UVW transforming, or sorry, XYZ transforming over to UVW, or you can go in both directions. So that's what it looks like in 2 dimensions. So you have, in 3 dimensions. That's what it looks like in 3 dimensions. So you have on page 819 the formula for the three-dimensional Jacobian. Again, alphabetical order, both directions. So top row X, then Y, then Z, and then going this way U, V, W. So always alphabetical. And then you would do this like you do a cross product. So I'll show you with an example, but you would do this just like you would do a normal cross product, except these are in the place of I, J, and K. It's like what you were doing with the scalar triple products. Remember with the scalar triple products from chapter 11, how you had numbers or functions in all 3 pieces? It's like that. That's how you would do it. So again, you can go back and look at this stuff on page 819, showing you why you have an R that pops up with cylindrical and why you have a rho squared sine phi that pops up with spherical. So it's interesting to see how it connects to what we were doing before. And then they have a 3-dimensional example, example 5. So again, because this is kind of a little weird, if you feel confused, just look at the examples in the book after you watch the video so that you're prepared to do this for the homework. Okay, my headphones are falling off. Sorry. Oh, I should show, well, no, I'll show you later. You know, I told you in a previous video, my husband was pressure spraying the deck. We finally painted it, that dark brown color, we painted it. I had to help him paint, and it's this deck over stuff, which is sort of like paint, but really, really thick. So it's like painting with chocolate pudding. So I spent several hours painting with chocolate pudding. It was very interesting. I wish it actually was chocolate pudding. I would have just eaten it, but it was paint. It smelled terrible. So just looked like chocolate pudding, but looks are deceiving. So I'll show you it later. I'll show you the 4th of July project later too. Well, I won't show it to you because it's not finished, but I'll tell you about it later, and then I'll show it to you in another video. So super great things going on in my house this weekend. It's all work, which kind of stinks, but at least stuff's getting done, and that's always a good thing. So here's my notes, 14.8. I separated it out. Here's all the 2-dimensional stuff. So I just kind of drew crazy little pictures just to show you these regions. They again are, when you switch from one to the other, they don't stay the same shape. They change shape. So I just kind of scribbled something. So they kind of almost look the same because they're just scribbled, but they're in general not the same shape. But you have, remember, R in the XY plane, G in the UV plane. And then when you change over, remember you have this Jacobian. So here I just wrote dA to remind you that it could have been dx dy or dy dx. And here it can be du dv or dv du. So here's the 2-dimensional Jacobian. All right, and so here's the three-dimensional stuff. Ugh, papers never cooperate with me. Okay, again, I just kind of drew pictures like they had in the book. And again, they look the same shape, but they don't have to stay the same shape when you do the transformation. So you've got D in the XYZ plane, G in the UVW plane. I mean, not plane, these are space. XYZ space, UVW, it's three-dimensional. And so again, here I just put dV. That could have been dx, dy, dz, dy. I mean, it's five other possible combinations, 6 total of that, what that could have been. And same thing here, 6 possible orders for what this could be, du, dv, dw, or you can switch them all up, 6 possibilities total for the order. And then here's the Jacobian. I didn't show kind of how it would look because again, it's just like a scalar triple product, and we'll look at it with an example, but this is all the formulas. So now let's look at some examples. Hold on, find what page this is on in the book. So page 821. Page 821, we're going to start with number 4. Okay, so number 4, it says solve the system for x and y in terms of u and v, then find the value of the Jacobian. That's part A. Part B, find the image under the transformation. That just means find the new picture, right? So you can go from R to G or from G to R. Those are the regions that you're drawing. That's what they're talking about by images there. And then they give you the boundaries, and then they want you to sketch it in the UV plane. All right, so I wrote the steps. I wrote it in words on this first one just because this is kind of a little weird. It's not solving a system of equations like you normally solve a system of equations, because normally to solve a system of equations, you'd have a number here and a number here, and then you would do either elimination or substitution. But this is different because we don't have numbers there. So what we're doing is we're having to take this and this, that is u equals a function of x and y, and v equals a function of x and y, and we want x to equal a function of u and v, and y to equal a function of u and v. There's more than one way to do this. This is not the only way. So if you kind of already had in your mind a way to do it, and you want to try it your way, and then compare it to mine, this is not the only way. This is just the method that works for me. I didn't even look to see which way the book does it, but this is the way I do it. So step 1 in this process, you're going to take these two equations that you have here, and you're going to solve this for x, and then solve it for y. Then you're going to solve this for x, and then solve it for y. All right, so for the u, take the u, solve it for x, I get this. Then take the u and solve it for y, and I get this. And then for the v, solve it for x, and then solve it for y. So now you have these 4 equations. 2 of them are x's and 2 of them are y's. So you're going to take the 2 x equations, set them equal to each other. That means the x's will be gone. And then you're going to solve for y. Then you're going to take the 2 y equations and set them equal to each other. So the y's will be gone. And you're going to solve for x. So take the 2 x equations, set them equal to each other. So it was this x1 and this x1. Set them equal to each other and solve for y. And then notice now y is a function of u and v. And then you're going to take the 2 y's, this one and this one, set them equal to each other, solve for x. Notice x is a function of u and v. I highly recommend when you do this that you write them alphabetically. Like here you have u first and then v, u first and then v. If you write them alphabetically, it'll keep you from making careless mistakes when you do your Jacobian. So that would be a good idea. All right, so for the Jacobian, you're going to the x first. So I have them backwards here. I have the x on the right. But the x is first. You're going to take the derivative with respect to u, which is -1, v, which is -3. Then you're going to go the y derivative with respect to u is -1. Derivative with respect to v is -2. These are all numbers, so notice it's going to be just a number for my Jacobian because my derivatives are all constants. Do the cross product. So this times this minus this times this. And so you end up with -1. So that would be the Jacobian. That's the extra piece that's going to pop up. I'm not actually going to integrate this here, but let me just mention something while I'm thinking about it because I'll forget later. Here, see how the Jacobian is in absolute value bars? That's absolute value bars. It's not magnitude or anything because these aren't vectors. That's absolute value bars. So if I was going to integrate this, my Jacobian was -1, I would need to put it in absolute value bars and make it a 1. Okay, I think actually in another problem I do integrate this. I don't know, but not right here. Okay, back to the problem. Hold on. Okay, they give you functions of, or they give you equations in terms of x's and y's. So you've got 4 lines. Okay, 4 lines. So I started, I wrote them all down first. I started with looking at what it looked like in the xy plane, just because number 1, I wanted you to be able to see how they look different, and number 2, I'll show you in a minute. But here, you got to change it over to u's and v's. So x equals -3. You go back up here, x is this. So if x is this and x is -3, then you would set those equal to each other, or you can think about it as putting this in place of x, because x is this, so you put this in place of the x, and then you get it in an equation in terms of u's and v's. So here's my equation in terms of u's and v's. I put a little dot by it so I can find it later. X equals 0, you do the same thing. X is this, so you put that in place of the x, and so this is, here just, I made it a little bit easier, well, in that one too. I had negative, 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 so I just multiplied both sides of the equation by negative to make it positive. So same thing here, negative and negative, multiply through by negative, make it positive. That's just to make my life easier. That's not necessary. If you like your life to be complicated, you don't have to do that. Okay, y equals x. Go back up here, here's y. So you're gonna take this and put it in place of the y. And then we already knew this was x. And then notice what happens here when I solve for, when I try to get it, in a nicer form or simplify it, I get v equals 0. So that's going to be nice and easy. And then y equals x plus 1. Here's my y. Here's my x. Plus 1. Just clean it up a little bit, and I get v equals 1. So here's my 4 equations that I'm going to have to graph now in the UV plane. Okay, so those are my 4. Again, I just put little dots by them so I could find them. So there's where they are if you wanted to make sure you have them copied down somewhere. So here, come down here. Okay, in the UV plane, V is like the Y and U is like the X. So for graphing purposes, I solved them for V to make them easier to graph. They're solved for V. So here, this first one solved for V becomes this. The second one solved for V becomes this. And then these were already solved for V. So notice it becomes a parallelogram. So it was. They don't have to stay the same shape, but it was a parallelogram. And now it's a parallelogram, but notice they're not the same. See, they don't look the same. And so don't expect it to be the same. I mean, it doesn't even necessarily have to be the same shape. It doesn't have to be. It could have gone from a parallelogram to a who knows what, crazy rhombus or something. I don't know. It could have gone to anything. So it doesn't have to be the same shape. All right. So as another example of this, sorry, it's out of order. Number 2, you're gonna need this later. You have a homework problem. Hold on. Let me find which one it is. Where are you? Yeah, here we go. Number 13. Number 13 says use the transformation in exercise 2 to evaluate this integral. So I did exercise 2 for you, but it's one I want you to try by yourself. So I'm not going to show it to you yet. But number 2, same thing as what we were doing in number 4. So I want you to pause the video and try number 2 by yourself. Okay, so pause it now. All right, so hopefully you tried it by yourself. Here was the problem, so let's look at this. First step, you're going to solve u and v for x and y, so you should have gotten these. Then you're going to set the x's equal to each other, set the y's equal to each other. On the x's you solve for y, on the y's you solve for x, so you should have gotten these. Now I need my Jacobian, so I have the derivatives. Again, these are just numbers, that's not necessarily the case, but here. So my Jacobian, -1/3. So remember, when you do number 13, make sure to put the -1/3 in absolute value bars. So it's actually going to be 1/3. Don't use the -1/3. You'll have the negative of the correct answer. All right, so for part B, you had, they gave you these lines. They gave you this one like this for graphing purposes. I solved it for y. So it's this triangle. Okay. And then now I want to figure it out in terms of u's and v's. So here, I switched the equations over by substituting in for the, here's the x and here's the y. Substitute those in here. I get these 3 equations. And so it makes another triangle, but again, a different shaped one. It looks different. So you're going to need that for number 13. Okay, so make sure to write that down somewhere. If you don't normally take notes, first of all, shame on you. You should be taking notes. And second of all, you're going to need that for number 13. So make sure you write that down. All right. So number 8 is where we're going to use the number 4 that we did together. It says use the transformation in the parallelogram R in exercise 4 to evaluate the integral. So this is number 8 using the stuff from number 4. So notice I have to change. Okay, I'm going to integrate now over my new region G, which was, where is it? Oh, there it is. That's on the same page. There, that's my G. I guess I could have labeled it. I don't have a blue pen. G. That's my G. Okay, so that's my new region. I'll get to my bounds in a second. But here I've got to change my function also. So when I change my x, I substitute in for x. This is my x from number 4. Again, if you go back to number 4, there were the equations for x and y and number 4. So that's what I'm using. All right, and there's my y. Here, notice you're going to have to distribute this negative, so be careful. My Jacobian here is where I actually am evaluating it, so I do need to put it in absolute value bars. And then, so when you switch from the dx dy, that's where the Jacobian pops up. So from dx dy to the new one, the Jacobian pops up. And so I get, when I, what is that doing? Okay, sorry. When I distribute the negative, this all simplifies down to just negative 2, well, this simplifies down to negative v, and then when I multiply by the 2, it's negative 2v. So this is just negative v times 2 is negative 2v. So notice in the picture here, if you went with your arrow going vertically, notice that, hold on, let me get a pencil. Okay, notice that here you would have this line on the bottom and this on the top, but over here you'd have this line on the bottom and this on the top, so it's different. And so if you were going to do your arrow vertically, you would have to have 2 integrals. And who wants to do 2 integrals if you don't have to? So you don't want to have to do 2 integrals, which would be what you would have to do if it went vertically, which would be du dv. So instead you want to do, I don't know what I just said, but dv du would take 2 integrals. I'm not sure which one I said. But dv du would take 2 integrals, so you want to do it with du dv. Okay, so we're going to go horizontally. And horizontally on the left side of the arrow, I have this line. On the right side of the arrow, I have this line. So because I'm doing them in terms of, I have u's that are going first, I need u as a function of v. So I have to go back to these equations and solve them for u, because that's what I want now. So go back to these equations, solve them for u, and then I have this line on the left, this line on the right. My v's stay here between 0 and 1, so that would be my new bounds. Okay, so I've got the new bounds for my region G. I've got my new function. I've got my Jacobian that I took the absolute value of, and I'm doing du dv. Now it's just a basic integral, so this one's really simple to integrate. So I'll just show you this. Hopefully you can do this no problems on your own. And it's okay for these to be negative, not a problem, but your Jacobian needs to be positive. Okay, so if you had forgotten to make your Jacobian positive, you would have positive 3, which would be wrong. That's not okay. All right, let's try another one. 10. Part A, find the Jacobian. Part B, integrate. But you gotta change it first, obviously. Okay, so here's what I have. I already have x as a function of u and v and y as a function of u and v, so I can go straight to my Jacobian. So there's my Jacobian. Derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, derivative of y with respect to v, cross multiply. My Jacobian is u. Okay. All right, now I need to get my region so that I can get, did it ask me for that? Oh yeah, sketch region. I was like, why do I already have the bounds. Okay, oh no, I have the bounds. They gave me the bounds in terms of x and y. Just kidding, I don't already have the ones. I have the bounds, but they're in terms of x and y, and that's not what I need. So I do need the sketch region, but it told me to anyway. Okay, so u is between 1 and 2, and then u times v is between 1 and 2. So what we want to graph this in the uv plane, again, v plays the role of x. Sorry, just kidding. V plays the role of y. V plays the role of y, so we want to solve them for y. So take this and solve it for y, which is v, and take this and solve it for v, and so you have 1 over u and 2 over u. So I only drew the part in the first quadrant because it told me that u had to stay between 1 and 2. There would be other parts down here in the third quadrant, but I didn't include those because, again, u has to stay between 1 and 2. So here's my two curves. This is the 1 over u and this is the 2 over u. So in case you can't see with my finger, this bottom one, this one is 1 over u. This is 2 over u. And then because u has to stay between 1 and 2, I drew in these vertical lines, u equals 1, u equals 2. So this is my region G in the UV plane. All right, so this was my original integral. Now I've got to change the bounds, change the function, change the dy dx. So here, if you, and this is maybe not quite as obvious, but if you try to go left to right, see how down here you've got this curve on the left and this on the right, but up here you've got this line on the left and this curve on the right. So if you were going to do your arrow horizontally, you would need 2 integrals. And again, why would you do 2 if you can just do 1? So here, don't do it horizontally. You want to do it vertically, so you can do just 1. All right, so the if I'm going to do it vertically, the v's would go on the inside, so they can be v equals a function of u, which I've already got here. V equals a function of u. So on the bottom is 1 over u. On the top is 2 over u. And then the u stays between 1 and 2. So that's going to be my new bounds. This is the form that I'm using. I just wrote this so you don't forget the Jacobian, because it's easy to forget the Jacobian. All right, so here's my new bounds. For my function, my original function was y over x. So I put y, which is uv, over x, which is u. That's my new function. Here's my Jacobian. Technically, that should be in absolute value bars. That should be like that in absolute value bars. But because the u is already positive, since the u has to stay between 1 and 2, it really doesn't have to be. So that's why I didn't do that. But in general, because it's a variable and you don't know whether it's positive or not, you want to make sure to put in absolute value bars. Okay, so notice this u canceled with this u, so I have v times u, or here uv. Integrate with respect to v, plug in, simplify. Notice here, these are the same pieces, so I can subtract them. 4 minus 1 is 3, and then this u squared and this u, one of them will cancel, 1 over u, it's natural log, and plug in. So that's number 10. All right, so last one, I think. Yeah, I didn't want to lie to you. Okay, Jacobian for 3-dimensional transformation. So I'm going to do part A with you, and then I'm going to let you pause the video and do part B by yourself. So for the Jacobian, they gave me my functions already, x, y, and z as functions of u, v, and w. So you're just doing all these partial derivatives. So x with respect to each of the 3 variables, y with respect to each of the 3 variables, z with respect to each of the 3 variables. So you should end up with 9 partial derivatives. Put them into your Jacobian. All right, so x is the top row, y is the second row, z is the bottom row. Then, here's how you're going to set this up. This is, again, like the scalar triple product. You've got the cosine of v times these pieces. Okay, these pieces. So you do u cosine v times 1 minus 0 times 0. Then minus, and then you have sine v. It's down here. I couldn't fit it. Sine v times this part and this part. Why does it go dark like that sometimes? Anyway, so it would be negative u sine v times 1 minus 0 times 0. And then lastly, 0. Of course, that's just going to be 0, but just for the practice, I showed the work. It's just going to be 0. But 0, and it would be these pieces. So this times this minus this times this, which is just 0. All right, so simplifying, I get this, which I can factor u out from, and then cosine squared plus sine squared is just 1. So that ends up just being u. All right, so you try by yourself. Let me just keep my paper up. Cooperate with me. Okay, part B. Try part B by yourself. So pause the video, try part B. All right, hopefully you've already paused it. Let me tell you what the answer is, and I'll show you my work. The answer is 3. So see if you got 3. If not, here's the work. You have your partial derivatives. I wrote it different here just so it didn't take up so much room. Partials with x, partials with y, partials of z. So this is my Jacobian. And then I have these pieces. Notice these were both just 0, so you really didn't have to write them. I just wrote them so you could check your work. And then up here's the rest of it. So it's just 3. All right, so that's all from 14.8. It's also now finally the end. I told you in 14.7 that was the end of chapter 14. I totally lied to you because I was thinking chapter 13. And chapter 13 only had 7 sections. But chapter 14 has 8. And so that's finally the end. Here's the practice exercises. So I forgot to tell you about my 4th of July project. Do you remember the horrible blue tile in my sunroom? So for the 4th of July project, because my husband was off work on the 4th of July, we retiled the sunroom. So the blue tile is gone. Hooray, hooray. I hope you didn't love it because it's gone now. And so we still have to, we did the tile. We still have to do the grout and put the furniture back in there, and that's why I'm in the kitchen. But anyway, once we do the grout and put the furniture back in there, I'll show it to you because it's not finished yet. I'll also show you the deck that I painted. Well, we painted. My husband did most of it. So anyway, I think that's everything I needed to tell you about 14.8. So if you have any questions, just send me an email.